For most of you that don't know me, I'm Jerome Glisse. I'm working at Red Hat, mostly working on graphic and GPU stuff and whatnot. Usually, each year, I'm doing a talk on Radeon or something like that, Radeon driver or kernel Radeon driver or whatever. But this year, I want to talk about something else, something that's probably going to come down the line for everybody in the room in the next couple of years. And it's all about being able to use the same process array space on the GPU, exact same array process space that you have on your CPU. So I will briefly talk about motivation. They are pretty obvious, you will see. Then we'll talk about memory management, how it works in the Linux kernel, but a very brief overview, and I won't go into any details because it will take hours, basically. I will talk about the hardware solution that exists nowadays, that is mostly people inside the HSA Foundation. I will talk about a software solution to the problem too, and I will finish up with what kind of impact this will have on the graphic side and how useful it can be for us, well, for people like me that are really mostly coming from graphic side rather than the GPU compute side. So the motivation is really mostly about the middleman. Right now, whenever you do GPU compute stuff, you first allocate buffer for your GPU using a specific API. Right there is just GPU API because it's easier that way. So you allocate your buffer, you copy memory you want to use, you do your operation using shader execution, and then you get back your result from the GPU. And that means you need to move all your data around basically between the CPU and GPU. You lose all the hierarchy you can have on your data structure you have in memory. And if you want to mirror the same data structure on the GPU side, you need to rebuild all the same data structure on the GPU side, all, like if you have a free structure or if you have some kind of index, H-table, whatever, you will need to redo it on the GPU. And so it's really cumbersome and really painful to use GPU. The idea is basically to just do that. Just execute the shader and just give the pointer the exact same CPU pointer you use. On Linux, that does mean that suddenly all the memory you allocate through malloc or by mapping a file need to be able to be accessible by the GPU. And, well, that's about one of the talk. So, memory management. Memory management is, for obvious reasons, massively concurrent. So whenever you have a program with several threads, you want that each thread of your program being able to work no matter what the other thread are doing. So at any point in time, all the other threads can map memory. They can go through memory pressure. So for whatever reason, if you're running low on memory, the Linux kernel can say, well, you are using too many pages. I'm going to take one page from you. So I will modify your page table, and you will go through a fault. So I'm just listing here a couple code paths basically on side the Linux kernel and most other operating system kernel actually. It's all this can happen at any point in time and in parallel, like concurrently. The deduplication stuff is mostly for the virtualization people. So when you have several guests on host operating system, most of the time, most of these guests will actually have many common files. So we will have like the same libc, for instance, and instead of having 10 copies of libc because you need one copy of libc for each of your guests, well, you rather want not to. So instead of doing it at the file system level, Linux does it at the page level. So that's why we have the KSM infrastructure basically. In not so recent, but last few years, there is also the Numa Architecture basically. So you have several cores on CPU. Each of them are linked to a memory controller. And so there's like a topology on CPU between the memory and memory controller and channel and bandwidth you can get and all. So that means like if your thread is running on one CPU core, you also want that the data the thread uses to be actually close to the CPU. There is compaction stuff also, so it's mostly used by few folks, for instance Google. So instead of swapping out your memory to a disk, you actually swap out your memory to memory, but you compress the memory on the way. It's useful. And the obvious thing is like, the more memory pressure you have on your system, the more there is program running, the more you're getting low on memory, the more concurrent operation will actually happen inside all the process page table. So the more difficult you get, the more concurrent you get, and it's like an endless cycle of life. But of course, you still need synchronization. You still need to be coherent. So you still need to go through the memory model you abide to. So that means like you need to have synchronization of some sort. The synchronization point inside Linux kernel is basically the page table. The page table is like the repository of all the page you use. It's what is actual data you're using. Obviously, the concurrency stuff implies no serialization. So whenever you want to modify a page table, you don't want to serialize all the people that want to do a modification. You don't want one thread to wait for another thread because the other thread is doing a modification too. You just want to do the modification right away and be able to resume whatever computation you were about to do. So page table is a synchronization point, and the idiom that Linux kernel is using basically is a very simple one. Whenever you want to do a modification to a page table, what you do is you look at the page table entry, the PTE, you save it somewhere. You perform the job you want to do, so like you want to swipe some page to the disk, for instance, you write it to the disk, and then once you're done with your job, you look back at the page table, and if the page table is still using the same entry as you were when you begin to do anything, then you just update the page table entry, set to whatever new information you want to set it, and go along. And if the page table entry is different from the one you used to see when you begin your operation, that means someone else actually raced with you and was the winner of the race, basically, was able to update the page table before you. So that means you have to back off and to undo whatever you've done, basically. So this is the very simple way Linux kernel does synchronization, basically. It's a vulgarization, so there's definitely many aspects to that and many variation in the way it's done. The important outcome that is like the page backing address inside the process. The page where the data actually is inside the process. It can change at any time. So that means when you look at this address inside the program, at one point in time it can be inside this page, but the very next few milliseconds it can be inside a completely different page. And you have absolutely no way to know when this kind of thing does happen. The fact that you don't know is really frustrating for what I'm trying to do. And obviously, what you can do is like binding memory will seem the obvious solution, but it's definitely not something you want to do because like you don't want to bind 4 GB or 16 GB of memory. And binding memory is like defeating the memory management point, basically. Pinning. Yeah, pinning. You also don't want to take reference on the page, basically. So it's something we do in the graphics stack right now. Right now, whenever we want to copy from user space, we take reference on the data because when we get the IOCTL, we know that the memory we want will be at the very worst case will be a snapshot of the data that user space wanted to give us. But you don't want to take references, any new references, basically, than the one you can take visual. So you don't want pinning, you don't want to take references, you don't want basically to modify the way the Linux kernel does memory management. You don't want to change anything in the logic behind the Linux kernel. So it was an issue also for virtualization people. So when you have a guest operating system, the guest operating system is managing actually a bunch of page tables for all the process running inside the guest. But at the same time, the host operating system is also managing the actual page and the actual memory that all the guests are using. So that means at the same time, at some point in time, the host operating system can make a decision, but the guest operating system can also make a decision. And if you want any kind of efficiency doing virtualization, you definitely want to have the guest and the host operating system to have some kind of channel to communicate with each other so that they can synchronize themselves about what they want to do about the page table of a process and how they want to reclaim memory. And sometimes the guest operating system will know, well, I can kill this process because this process is not really important for my use case and for whatever I'm doing. But the host operating system have absolutely no idea about that. But at the same time, the host operating system know about all the guest operating systems. So you can know, well, I can migrate this guest operating system to some other computer. So basically for efficiency, you need communication. And this is the main reason why a new API was introduced inside the Linux kernel. It was the MMU notifier API. It's basically a very simple API that basically bracket any kind of change you do to the process page table by just calling. So you can register a callback basically, and whenever there is a change to page table, you get this callback that tell you, hey, I'm about to change the page table. And you don't know exactly what's going to happen, but you have a small clue about something's going to happen. It does allow you also do proper uniqueness and all like dutiness and accounting and all. It's mostly for staying coherent with the Linux assumption. But again, this API does not enforce serialization. At any point in time, there can be several notifications on overlapping range of memory. So it's like a step forward. It's basically whenever you want to change something, you just cry out loud that you're going to do a change. If somebody is listening, somebody is listening. If nobody is listening, nobody is listening, and it goes on. So the end game basically is that the page table is a constantly moving target. You never know what it's going to be. It can change at any point in time. And the page behavior address is the basic issue you have whenever you want to mirror a processor space. You want the GPU, the devices, and the CPU to use the same page for the same address. You don't want them to get out of synchronization. So that's the cornerstone, basically, of being able to mirror processor space, is being able to have both on the CPU and on the GPU a coherent view of the page table to know exactly what page you want to use, to know exactly for this address, this is where I want to write my data, actually. And again, no pinning, no references. You don't want to change the way the Linux kernel does work. You don't want to change to write basically all the memory management there exists, because it's years and years of artwork and customization. So when you get there, basically, you have two solutions. You have an hardware solution, which is what most people would expect, I guess. And you also have a software solution to the issue. A software solution that also, of course, need a bunch of hardware capabilities. You cannot do it with any kind of hardware. So I will first go over the hardware solution briefly and see what exactly it does, what you can do with that, how it does works, and then we'll go over the software solution. So at the beginning, I was talking about middleman. The middleman was this API you have to use to copy memory from the CPU to the GPU. And IOMMU is basically a new middleman. It's between your device and your memory. It was first introduced because of virtualization and other issues like scatter gather. You also wanted to do input-output protection on memory range. You wanted to be able to isolate devices when you were inside a virtualization environment. Well, there was several things where IOMMU is really, really nice to have. But one of the other things about IOMMU is that it's inside a unique position. It's between your devices and the memory. It's the middleman. You have to go through the IOMMU on modern hardware, x86, and most modern ARM too, because there is most of the time there is also an I/O MMU between your device and the memory. It's very close to the CPU since most of the memory control have been included on the die with the CPU. It's the same technology most of the time. Well, not most of the time. Nowadays, the I/O MMU is designed by the exact same person that actually designed the CPU. Well, different team, but same company. So that means the I/O MMU is able to understand the CPU page table format. And that means the I/O MMU can share a bunch of blocks with the CPU, like the TLB cache, for instance. And basically, the I/O MMU is now capable of working your page table if you want. You can make an I/O MMU that does that, then AMD does that, actually. So the solution was actually drafted into specification for the PCI Express. And it's a couple of extensions to PCI Express, basically. The first one is very simple, very obvious. It's a process address space unique identifier, basically. So for each PCI Express transaction you do with the root complex, you can say, I'm doing a transaction and I'm only interested with this process array space. This transaction is about this process array space. And you give this unique ID inside the transaction, inside the PCI Express transaction. And this just basically tells the I/O MMU, okay, you're looking at this process array space, so you want to use this page table. And the other part, the other side of the extension is the address translation services. And it's also very simple. You just tell the I/O MMU, okay, I'm looking at this process array space and I want to access this address, this virtual address inside the memory of the process array space. What the I/O MMU will do, it will go over the page table that is the CPU page table of your process, the usual page table. It's not a new one. It will walk down the page table, find the page, and give you the answer with something your device can access. Of course, you don't want to do that any single time you want to access one page or another page. So you have a TLB cache on the device that cache all the lastest transaction, all the lastest page you were accessing, and so you don't have to ask the I/O MMU, please give me the address, the page address I want for this address. But at the same time, whenever there is some kind of invalidation going on, so whenever the CPU process page table is updated, you don't want the devices to keep using the old TLB cache. It does that, so there is like a synchronization inside the PCI Express extension that basically say, forget about your TLB cache, it's gonna change right now. Also, you want to carry over all the protection stuff, so this page is read-only, this page you can write it, you can execute code, or all the protection you can think about. And you also want to carry over things like dirtiness, youngness, and is this page been accessed or not? Does anybody did write to this page or not? So it's the I/O MMU hardware solution. It's really easy. You don't have to do anything from the driver point of view at most. Pretty much the only thing you need to do is like your driver needs to register the process address space. So whenever you want to mirror a process on the device, you call this API that say, give me a unique identifier for this process address space. Here's the page table, and you're just set from that point on. So on the device, there is two ways. Well, there is several variations between these two ways. There is two big ways you can use this process address space stuff. The first way is very simple. You have a page table on your devices, and you have a special bit inside this page table, a special bit flag inside each entry inside the page table. And this bit flag tells you, well, if I'm set, use the ATS PIS ID and go over the PCI Express I/O MMU and do a translation there and cache the stuff inside your TLB cache. This is a very flexible solution because that means you can intervene mirror address space with non-mirror address space. So you can have like, okay, I'm gonna mirror the first 2 GB of my address space and the rest I'm gonna use it for something else. Thing is, by doing a single flag for each page table entry, It makes the whole memory controller for devices and the whole TLB cache much more complex than you wish it to be. The other more simpler approach is basically to use some kind of aperture on your devices. So you say whatever address falls into that range, go use the PSID, go use the IOMU to do a translation for me and give me back the hardware address I should use. And same goes around for when you are outside or vice versa. It's not very flexible. There is a very coarse granularity when you do an aperture approach to using PSID. But on the other end, you get a lot simpler memory controller, a lot simpler TLB cache too. So this is a device side, like kind of depending on what you want to do. The aperture stuff can be very, very interesting. But if you really want to take advantage of video memory, for instance, you really want to have the page table solution, which is much more complex. So whatever you look at this solution, in whatever way you look at it, it's basically a one-way communication. It's always the devices that ask the IOMMU what is the current state on the CPU page table. You cannot copy or move anything inside the video memory temporarily, just because like you're going to do something on this 4 GB of data memory and you're going to crunch it for 1 hour, and after that you will spit 1 page of results. So you probably don't want to have the memory sitting inside system memory for 1 hour, but you probably want it on the video memory. And it's not something you can do with the hardware solution. There is also a couple of limitations on the IOM2 V2 implementation of AMD. It's often the case when you are working in a software company, you're like, why the hell does the hardware people didn't do that way, because it will be a lot simpler and you will have to go through that. So when you have, so two deficiencies also is like you add latency, of course. Whenever you do a PCI Express transaction, there is latency, but whenever your IOMMU and PCI Express transaction also do have to do a page table walk, beside another more level latency to all your transaction. And the other thing also is that whenever you do PCI Express transaction, you now have this PCI, PICID, and ETS stuff, so you have less bandwidth than you used to. But the issue with the update is the biggest issue I see right now with the IOMMU V2 is that whenever there is a page table update, what does the IOMMU V2 driver does is very dumb. It points the IOMMU to an empty page table, flush all the cache, and for the duration of the page table update, it can be like a disk write to some weird controllers that takes long. Nothing can happen. So you have to wait for the page table update to go through. Once the page table update did go through, you program back the page table. So you had this huge latency that is not bound by anything. There is no boundary on how long it will take for this operation to complete. And it will have been solvable very simply, like you only need a new flag inside your CPU page table. It's a flag you set before you do any update. You say, this range of memory, don't trust it. I'm going to do something about it. I don't know what yet, but something going to happen. And once you're done with the update, you unset the flag and suddenly it works. So doing that basically allows your GPU to keep working on address space that are not changing basically. Most of the time you won't have any change on the address space. But right now, whenever there is a signature, and even if it's not something the GPU is actually using, a GPU will have to wait current implementation. So there is a bunch of limitations with doing everything inside the hardware. It's very nice because it's very easy. You don't have to do any real modification to your driver or to your code. But as you can see, you cannot do everything. So one other thing about GPU too is that they are like definitely video memory junkies basically. It's never fast enough, and there is never enough bandwidth for a GPU. Well, it's not mostly for GPU, but mostly for the applications that run on GPU. Yeah, GPU they really crave for bandwidth, and when you look at video memory, it's up to 200 GB per second on the GPU, Ion GPU, the GDR5, and several channel. But for system memory, it's 20 gigabytes, so it's like tenfold slower. So you definitely, when you want to crunch number, you want to use video memory. And if you want process array space, transparent process array space, you also want to use video memory because, well, otherwise what you will do is basically waste the system memory bandwidth. The latency too. The latency is a lot higher if you use the system memory. I will already explain a little bit why, because you need to go through the IOMU, you need to do a page table walk, you need to do PCI Express transaction, and you need to wait. How long, you don't know. But with video memory, you know the latency, and it's very lot smaller than whatever you can get with PCI Express transaction. I don't think any bandwidth like the 200 gigabytes will happen anytime soon on any consumer product beside PS4, or PS4 being pretty much the only one. I don't expect to see motherboard with GDDR5 DIMM. I don't know, like we're told some company or OEM are talking about shipping such kind of motherboard where you can plug in GDDR5 and instead of GDDR3. The software solution, on the other hand, basically allows you to use the video memory. It requires change within Linux kernel, obviously. We can almost know about video memory. It doesn't need to know too much, actually, about video memory. It doesn't need to manage video memory for you. You only need to know, like, give me a middleman to who I can talk to who I can ask to. You can basically need to be able to ask the device driver, please, you have this data inside your video memory. Give it me, write it back inside system memory in this page because the CPU need to access it. It's not exclusive with the hardware solution, so you can have the hardware solution that work for everything that's still in system memory, and at the same time use this software solution for everything you want to move over the video memory. And that's basically what I've been working on lately. I've been working on a software solution inside the Linux kernel to be able to mirror the address space on any devices. It was mostly done because I'm a graphic guy. It was mostly done with the GPU inside my mind, but it's also useful for other devices, and quite strangely, InfiniBand devices, for instance, network device, also interested in such kind of thing. So the challenge when you do this software solution, there are several of them. You cannot update the device page table from the CPU. That's a big one. You need to have serialization between the CPU and the device. So when you do a change to the CPU page table, you want to make sure that before the change is actually used by the CPU, the exact same change is actually also in effect on the devices. So this is the page table currency, basically. The same page breaking, the same address on the devices and on the CPU at any point in time. Thing is, when you do serialization, it can really hurt performances badly, basically, because that means that one might need to wait on the other, and you have no expectation on what the other might do and how long it might wait. But it's a cost. So it's a cost. Either you're ready to pay for it and to maybe take advantages of the GPU power crunching number. There is no way around, basically, no way around doing some kind of serialization between the CPU and devices. There is no way I can think of, unless you have a device page table update from the CPU. The plan originally was basically to minimize the number of changes we want to do to the core memory management stuff. We didn't want to be invasive. We didn't want to suddenly rewrite the whole directory or rewrite the overall file system page cache stuff. We didn't want to touch that. We also didn't want to be disruptive in any way. We didn't want to suddenly move code all around everywhere, add a bunch of if-else in every places. We wanted to be as much as, I don't know, like, we really wanted to be able to disable a feature for anybody that doesn't want to suffer the cost, and to be as little disruptive with other things in the Linux kernel. And there is a bunch of other difficulty, like there is a bunch of new API inside Linux kernel, like memory C group, and for instance. What does happen when you migrate a page to video memory? Do you want to echo the page against the system memory still? What kind of modification do you want to make to the memory C group stuff. And there is a bunch of other API where you are like facing some kind of philosophical question about this API was always designed with the idea like that it will always be a page inside system memory. So it's one of the big challenges. And it's also at another point of failure. So most of the time when you use, for instance, a file, you can have one of your disk die or one of your I/O controller die for whatever reason, and suddenly you have a file inside memory that you cannot write back to disk, or you have a file that can get corrupted badly. And whenever you have your file inside the video memory, if your GPU suddenly lock up or whatever other thing that might happen to a GPU, well, you might not be able to get your data back at any point in time, so you might lose your data inside video memory forever. So that's another point of failure. So again, it's how do you report to the user space up to all the levels? Do you want it to report like a I/O issue, some other stuff? And again, we didn't want to have to change too many things inside the whole Linux ecosystem for memory management. So this was all the goal we wanted to achieve when we were working on the software solution. It's a partnership we have been doing between NVIDIA and Red Hat. We have a working prototype. We are hoping to send, well, I'm hoping to send very soon the patch set upstream for discussion in coming weeks. And from then on, my big hope is like it can be useful to other people. As I said, I know that devices like network controller are also interested in similar solution. I don't want to go too much into details about the implementation because it will be like going over all the code basically and all the file system code too, and it's definitely not something you want to be doing ever in your life. But like I said, we want to have an agnostic API. So the API is really simple. From my point of view, it's mostly an extension to the MMU notifier API. So for anybody familiar with the MMU notifier API, it's an extension to it. It gives you new entry point, new callback, new function you can call. It gives you a new, hey, please handle this page fault that happened on the device and tell the device what page to use for this address. There is a bunch of requirements on the hardware. So if you want to use that API, your hardware needs to be able to do to have a page table and a true page fault. So to be able to stop doing any execution on the process, on all the threads that access the memory where the page fault is occurring. So it's like a CPU. Like, you know, when you talk about true page fault on a CPU, it has been around for so many years. That sounds so easy to do. But on a GPU, a page fault and a true page fault where you stop thousands of units when you say stop and let me do something. It's like wasting. You cannot easily switch this thousands of units to a new context and say, well, while the fault is going on, let me do some computation for this other process where I can work on. So it's not as easy as it sounds on the GPU side than it is on the CPU side. One big thing also needs to be able to support read-only. Like read-only is so used in so many places inside the kernel, Linux kernel, inside the Unix API, inside the whole APIs, that read-only is like the strict minimum stuff you need to be able to have inside a page table. Being able to be preemptible too, so you want to be able, like if you have a CPU page fault on something that inside video memory, you want to be able to say to the GPU, please stop doing anything with that memory, let me move it back to system memory. And once I'm done moving back to system memory, you can use system memory instead of video memory. Other than that, you can have a lot of differences. You can have different page size on your devices. There's a lot of things you can have differently. There is a couple of other things that are really, really important to have. If you have them, it's really a big bonus. Being able to set a duty flag, so whenever your GPU or device is writing to memory, being able to mirror the fact that something has been written to the page inside a page table, so there can be some kind of dirtiness accounting. Fast preemption, so that the CPU doesn't have to wait 10 seconds for a page fault. And also fast device page table update. But there is a bunch of other things that are really nice to have that can simplify the API. But again, we want it to cover a big ground, basically, of device that can take advantage of this API. So the command monitor is basically the first few points I gave. For the graphic, so as I say, I'm a graphic guy. And I think it's going to be very useful, and I think it's going to happen very fast. The first obvious thing is like texture upload. Don't do MEMS API anymore. If you have a new API, new GLA extension API that say this is the pointer to my texture, use that. The next Sparse texture extension with automatic load from disk. This is a file where my texture is. Use that. And it can be a 20 gigabyte file of texture and page in whatever is, well, it's never the right format, but you can. You can make it happen. Like on some GPU, there is what we call a prefetch parser that can basically do JPEG decompression, that can do tying stuff and all. So it's doable. Yeah, we haven't seen it, but like, I mean, it's doable inside the VRWare to have some kind of engine that first marsh model, basically the data for you. Yep.
Yeah, most of the time you can't do texture upload without some sort of messing with the data, but
yep.
There are applications that are built directly for your stack because they know what hardware is shipping. For example, Chrome OS on Intel hardware. On that hardware, they know what texture formats we natively support, and they upload data in a format that the hardware natively supports, so we could possibly avoid mem copying for that when the applications are written directly for your hardware.
Mm.
Yeah. Oh, yeah, tiling format. Never mind.
But my point is mostly like right now, I completely agree that right now it's not something doable. But I believe that at one point in time, maybe in the future, there will be some kind of API that say, hey, if you want to be able to use directly this texture, you need to use this common format that everybody agrees on. Yeah, I'm naive.
I mean, as far as I know, DirectX 11.2 should have some support for so mega textures, whatever they call it. Like that would be probably be streaming.
Yeah, but it doesn't enforce any common storage format, any common.
And there's already the AMD Sparse texture extension for GL that's probably not exactly the same, but it's the same idea. Yeah, and so basically what that lets you do is that your textures are defined in these large kind of page-size blocks, and you can tell it, this chunk of the texture, there's not actually anything there. Don't back that with anything. And then when you try to access that from a shader, there's a couple different ways that you can access it. I think the way that they do it is the texture lookup function has an out parameter where your data goes, and it returns you a Boolean that is, yes, you got some data, or no, there was nothing there. You sort out what to do.
Yeah. And well, I still think there will be a bunch of specific cases where you want to have a specific API for the graphic side, where you want, for instance, set cache policy because you know that your front buffer, you should not read from the front buffer. Like something, again, we have been trying to tell everybody to not read from the front buffer. So if you don't have any read from the front buffer, if it's on cache, it will be a lot faster. Or write combine, actually, will be a lot faster than on cache. So, and I think the biggest use case will be for GL compute shader. if you can have the exact same hierarchy, structure hierarchy that you load from your program inside your shader, being able to access it transparently from your shader without doing any kind of modification or without having a duplication between your memory object, between your memory object inside CPU for your CPU and memory object you access for the GPU. It will be really, really, I think, something very useful, I believe. So on the graphic side, it's pretty much, hand-waving about all this cool stuff we can do. It would require a lot of agreement between a lot of different people, so I wish it will happen, probably won't. I believe the compute shader part will be definitely the one that will happen first, if any of them. And I guess my last comment is basically a question, mostly to Intel. Are you working on something like that, or are you interested in a solution like that? Which is like I know the question. So on the NV side, you can buy the hardware right now, the hardware with the IOMU V2. And you can also buy devices that does support the ATS and PSID. There is just no, as far as I know, there is no open documentation to tell you how to use it. Yeah, but I just wanted to say we're been working on that. We will be sending a patch very soon. If it's something you're working on, we would really like to have feedback on whatever we're doing. And if it's useful to you, yeah. You are on the same die. Yeah. But like EMD is in the same situation as you, but we're using an IOMMU between them and GPU, but it's like, yeah, cannot say much more than that. NVIDIA is probably very close to what you have, actually.
I mean, we already have a page table for our GPU in all Intel hardware since the 830. And it's fully mutable, and it just happens to be a one-level linear page table, so it can't be the CPU page table, and it happens to be only 2 gigabytes instead of 48 gigabytes, whatever the current address size is. It's bigger than that, isn't it? It's 36 bits or something. What is crazy amount of our memory? The restriction that we have currently is that we don't get any page faults.
Yeah, and page fault is a big thing.
Right. And so the question I have is, yeah, it's a kind of a serious restriction. I guess the question is, how much of this common infrastructure is going to be relevant for how much of what we currently do with our GPU is relevant for examining in the context of a IOMMU based GPU that has a similar page table, right? Because most IOMMU based devices that I know for disk controllers, network controllers, and that kind of thing, they can't take a page fault either. The IOMMU has to be populated in order for that device to operate. Mm-hmm. And so we effectively have an IOMMU for our graphics devices today. We also have an IOMMU for them. That's a separate issue that doesn't actually work very well. So the infrastructure that you're building for the IOMMU v2 stuff seems like it should be effectively the same as what we currently use on our Intel GPUs today. Is there a significant difference?
It's not the same. So what you can do right now today is basically you do a get users page. You take a reference on the page. Whenever you get an IOCTL, for instance, you want to update memory from system memory, you can get user page. Take a reference on the page. Whatever happened at that point in time inside the process page table address space, you don't care, because basically
Right.
You just take a snapshot of memory from the process address space.
Right, you pin all the pages, map them to the GPU, and go.
Use them, go, and,
Right.
and pin and take the references. So no, there is no. It's not useful if you don't have a page fault. You need to have page fault, and you need to want to have the exact same process address space.
It's right. You don't get the problem with the IOMMU is that it's also doesn't have the same address range as the CPU does.
You mean it doesn't have the same size for, like, it's not 64-bit, it's like 36-bit.
Right.
You need an IOMMU that supports 64-bit.
Right. So,
But like most of the AMD IOMMU, ARM IOMMU, well, next generation ARM IOMMU will have 64-bit.
Okay.
too. So then it's up to you. I mean, like, I'm a software guy, so this is what you need to do inside your hardware. And
so you're waiting for a 64-bit page tables before a lot of these questions become interesting.
it's usable on, so it's done to be usable on 32-bit architecture, but that means you can only mirror a 32-bit process array space. So it can still be useful if you're running a 32-bit process array space on a 64-bit kernel, but then you don't have this gigantic data set you want to crunch on the GPU.
Yeah.
So
kind of missing the point.
yeah.
Okay.
But, yeah, we didn't want to say this is a 64-bit only. So even if I don't think the 32-bit case is meaningful.
Cool.